Okay, so today we're going to be talking about homogeneous linear systems of differential equations. Okay, so these are differential equations that are in this form given here. So in this case, x is a vector, a is a square matrix, and x is a vector again. And this is actually the derivative of the vector x, okay, with respect to some variable. So in this case, you can kind of think about x as the vector of smaller variables like x1, x2, x3, so on. And when you do the derivative, we're taking the time derivative of each entry of that vector. And we're saying that the time derivative of this vector is equal to this matrix A here times itself. Okay, and that's using our matrix vector multiplication. A is the square matrix, and it's also a constant matrix in this case. So if you had other things going on in A, that would require different techniques than we're going to talk about today. So in this case, A is just a square matrix of numbers, constants. Okay. So just so me be clear here, A is some matrix. You could call it A11, A12, A13, A21, A22, A23, A31, A32, A33, where all these are numbers. Okay, this is a 3x3 case. You could have a 2x2 case where the vector is 2, and this is 2x2. You could have, any amount as long as it's square and it matches up correct lengths. Okay, so what's the idea? How do we solve this? The main idea here is that the eigenvalues and eigenvectors of A tell us about the solutions to this differential equation. So the eigenvalues and eigenvectors solve this equation. So A times a vector V, I write a little arrow here, equals lambda times that vector V. So we multiply a certain vector by A, we get a multiple of that vector. Okay, so the multiplication factor lambda is called the eigenvalue. And the vector V is the eigenvector. Okay. In general, the idea is very similar to when we had a constant coefficient case. And in that case, if you remember, we had the solutions were of the form e to the constant r times t. Okay, in this case, it's similar. The solutions are going to look like the eigenvector times e to the eigenvalue times t. Okay. In fact, and so that's the idea here. So if we find lambda and v, that tells us that the solutions look like are of this form here. Okay. So the idea here is we have, say, a 3x3 system. In this case, our general solution x is going to be a combination of three separate linearly independent solutions. Okay, it's going to be a combination of like c1 x1 plus c2 x2 plus c3 x3. All right, each of these solutions, they form a fundamental set of solutions. So they should be linearly independent. And each of these is going to correspond to an eigenvalue of the matrix A here. Okay, so it's a 3x3. That means we need three different solutions, and the eigenvalue has three eigenvalues, and so that's going to help us determine what each of these solutions are. Okay, so what can happen? So some different things can happen. We could have all real eigenvalues that are all different, and that's the simplest case. So say we have something like the eigenvalues are lambda 1, lambda 2, so on. In this 3x3 example, it could be lambda 3. Then the three solutions are x1 and they all have corresponding eigenvalue vectors, v1, v2, v3. x1 will be v1 times e to the lambda 1t. x2 will be v2 e to the lambda 2t, and then x3 will be v3 e to the lambda 3t. Okay. And we can kind of just check and see this. If we took the derivative of this with respect to time, so just say you had x1 derivative, you're going to get lambda 1 v1 e to the lambda 1 t. Okay, v is a constant, the vectors are constant, so when we do the time derivative, we just get an extra multiplication here. And if we also think about a times x1, we know v1 is an eigenvector with a corresponding eigenvalue lambda 1, so we would get the same thing. We get lambda 1 v1 e to the lambda 1 t. And this constant e to the lambda 1 t, that scalar value just hangs on there. So we see that that does solve this differential equation here. Okay, and so that's the idea of why we know they're of this form, because multiplying the solution is, we're looking for these things where we just get a constant multiple of the eigenvector here. All right, so that's one case. Sometimes, though, it doesn't work out nicely like this. Sometimes you get a repeated eigenvalue. So you might have a matrix where the eigenvalue lambda shows up multiple times. Okay? Maybe 2 or 3 times or more. And so in this case, all three eigenvalues, all three of them are the same value really, but they're represented 3 times. They have repeated multiplicity. So what happens in this case? In this case, there's a couple of possibilities. One is that this eigenvalue lambda has 3 different eigenvectors, v1, v2, v3, that are linearly independent. Okay, so that's one possibility. In this case, we end up basically the same solutions right here. You know, our x1 is still v1 e to the lambda t. So we get these same solutions, and each one has a different eigenvector associated with it. So x2 would be v2 e to the lambda t. X3 would be v3 e to the lambda t. Okay, so these eigenvectors are linearly independent. So these solutions, x1, x2, and x3 are linearly independent. Okay, even though they have the same exponential form. So that's possible. The other possibility is that we have a repeated eigenvalue. We can only find a single eigenvector. Okay, so what happens here? So we have lambda, but repeated multiple times, say twice, and we only have one eigenvector v. Okay, so in this case, the solution is given by something different. In this case, is very similar to what we did in the constant coefficient case. We have a constant times v1 t e to the lambda t plus another constant. But now we have a second vector v2 e to the lambda t. How do we find this v2? Okay, we can't find another eigenvector. The v2 solves a separate equation. We have to solve this equation. So before, to find v1, we solved a minus lambda I v1 equals 0. To find v2, you solve this equation. A minus lambda I v2 equals v1. So you're able to find an eigenvector solving this equation. Once you find that v1, you move it to the right-hand side and you resolve the equation again. Okay. Once you're solving this equation, you get v2, and that becomes your second part of your solution right here. Okay, and we multiply by t, our original eigenvector. If you had it repeated 3 times, you would do like a t squared over 2. You'd have to move v2 over and keep that process going. Okay, so again, this is available in your book, so this is something you can look up. All right, what's the last possibility? The last possibility is that you end up with a complex eigenvalue, and you'll always end up with pairs of eigenvalues. So it'd be something like alpha plus or minus beta I. So complex eigenvalues always come in pairs like this. Okay, eigenvectors v1, v2. All right, v1 is for alpha plus beta, and v2 would be alpha minus beta I. In this case, I mean, it's true that the solution could be written as in this, V1, and since the eigenvalue is complex, these V1 and V2 also have complex values. So it's true that the solutions could be written as V1 e to the alpha plus beta I and V2 e to the alpha minus beta I times t. So these are solutions, but they're complex solutions. Okay, we have a complex value in the exponential. These V1s and V2s have complex numbers in them. Okay, so these are complex solutions to the linear system. Okay, in most applications, you really only care about the real part of this. And so we can write this down in another way. We can write it as x1 is the real part of V1 times cosine beta t minus the imaginary part of V1 times sine of beta t, all of that times e to the alpha t. Okay, and then the second solution, x2 is the imaginary part of V1 times cosine beta t plus the real part of V1 sine of beta t, all times e to the alpha t. Okay, so those are our two solutions. But they're only real because we see we got rid of the I and the exponential, and these sines and cosines are a real part. So what does this imaginary real part mean? So say you have a number c plus d times I, and we want to take the real part of that. The real part is just the real number c. Okay. What if we want to take the imaginary part? The imaginary part of c plus d times I is the number d. Okay. Again, the imaginary part is a real number. It's just the real number constant in front of the I term. Okay, so real imaginary part of V1 gives you a real number. It just gives you whatever is in front of the I. The real part of a number, of a complex number, it just gives you the real part, the real constant. Okay, so in this case, V1 is a vector. So it's going to look like A plus B times I, C plus D times I. The real part of that vector is AC, and the imaginary part is the vector BD. Okay, so they're both real vectors. We just split it up into real and imaginary parts. Okay, so again, these two solutions here, I don't memorize them. Just look them up in your book or look them up online. But just be kind of aware, how do you compute these different parts? Okay, the other one thing to be careful of is, notice we only use V1 here. So we only use the eigenvector corresponding with alpha plus beta I. Okay, so if you found this works as long as you just pick one of your eigenvalues and you find its corresponding eigenvector. Okay, and that's what these vectors here, the eigenvector. And then the alpha is the real part, and then beta is the complex part, the imaginary part. But you need to make sure that it's written as alpha plus beta I. Okay, so this is corresponding to alpha plus beta I. So if you found the vector V2 corresponding to alpha minus beta I, then just make sure you write it as alpha plus negative beta. And so you'd use negative beta here everywhere you see a beta. Okay, make sure that you get the sign right. Okay, that's important. So that's kind of the nice thing about complex eigenvalues, is you find, they come in pairs. You only really have to find one of the eigenvectors, and once you have that, then you have two solutions. Okay, because there's this relationship between the complex pair of eigenvalues and eigenvectors. All right, it gives you two solutions, you've only found one eigenvector. Okay, you don't actually need to know what V2 is. Okay, it turns out they're basically the same. They're just flipping some negatives, and that's why this nice relationship works out. All right. So let's try some examples of how do you solve these types of equations. All right, so we have this system here. Derivative of x equals this matrix times x. So what's the idea? We need to find, this is our matrix A. We need to find its eigenvalues and eigenvectors. So how do we do that? The eigenvalues solve the following equation. They solve that the determinant of A minus lambda times the identity matrix equals 0. Okay, they solve this equation. So we need to write down this. We basically have the determinant A minus lambda I. So we take all the diagonals and we subtract lambda from them. So we have minus 1 minus lambda, 1, 0. We have 1, 2 minus lambda, 1, 0, 3, minus 1 minus lambda. So the determinant of that matrix should be 0. We need to find what lambda makes that determinant 0. Okay. So you could find the determinant of this matrix a couple of different ways. What I'll do right now is I'll go along the diagonals. So I multiply along the left to right going diagonals and add those. So we have negative 1 minus lambda, 2 minus lambda times negative 1 minus lambda. And then you have plus this second diagonal, 1, 1, 0, that's 0, plus another 0, 0, 0, 1, 3, that's also 0, okay. And then you might subtract the backwards going diagonals. So we have a 0 on the main diagonal. We have 1, 1, negative 1 minus lambda, so minus that. So minus lambda. And then we have minus negative 1 minus lambda times 1 times 3. Okay, so that whole thing should be 0. We want to solve that for lambda. A nice thing happens is we have this negative 1 minus lambda everywhere, so I can factor that out. So what do we have left? We have negative 1 minus lambda, 2 minus lambda, negative 1 minus lambda. Okay, those are gone. We have a minus 1, and we have a minus 3. Okay, and then if we distribute this part out, we can't factor anything. Let's see, we have negative lambda, that's positive lambda squared. We have a negative 2 lambda plus 1 lambda is minus lambda. And then we have a minus 2, minus 1, minus 3. So that's going to be minus 6. And we solve this term, minus 1 minus lambda. All right, so can we factor this parabola here? Yes, we can. It's going to be lambda minus 3, lambda plus 2. Right, so 2 minus 3 multiplied equals negative 6. 2 plus negative 3 is negative 1. So that all works out. So that shows us that lambda is either equal to minus 1, okay, that turns out to 0, positive 3, that turns out to 0, or minus 2. Those are our three eigenvalues. Negative 1, 3, and 2, negative 2. All right, so that's the first step. Okay, these are pretty long problems. So the next step is, based on our previous work, we just need to find these eigenvectors now. V1, V2, V3. Once we find those, then we know exactly what the general solution is. Okay. So how do we find an eigenvector? An eigenvector means we need to solve this vector equation. A minus lambda I times a vector V equals 0. So we plug in the lambda that we know and try and solve for V for this equation. Okay. So let's see, how do we do that? Let me start with, let's try and find lambda for negative 1. So the matrix, in this case, A minus lambda I, looks like following. We plug in lambda everywhere here. Let's see what we get. So negative 1 minus negative 1 is 0. We'll get 0, 1, 0. Get 1, 3, 1. And we'll get 0, 3, 0. So that times a vector v1, v2, v3 should equal the 0 vector. Okay, we're trying to solve for these entries here, v1, v2, v3. So note, whenever I don't write the arrow, these are just numbers now. Okay, so keep that straight from versus the vectors v1, v2, v3, which are each eigenvectors. Okay, these are just numbers here, part of the eigenvector. So there are lots of different ways to solve this system. Okay, you could like compute the matrix inverse, different things like that. You could do row operations. What I find to be the easiest in this case, especially if you're not super familiar with linear algebra, is just to write these as equations and not as a matrix equation. So what does this really say? This is as 0 times v1 plus 1 times v2 plus 0 times v3 equals 0. Okay, or in other words, 1 times v2, so v2 equals 0. Right, that's what the first row says. Second row says v1 plus 3v2 plus v3 equals 0. And the last one says 0v1, 3v2 plus 0v3 equals 0. Okay, so when you're finding eigenvectors, okay, we're trying to solve for v. One thing that should always happen is that one of these equations should basically drop out, should be redundant. Okay, that should always happen. Okay, because in fact, there's not just a single eigenvector v, there's actually a whole family of eigenvectors v. So whenever you're solving for an eigenvector, you're going to have to make a choice at some point. Okay, so which generally means if you have 3 equations and 3 unknowns, it means one of your equations is redundant. You don't actually need that equation. Okay, so in this case, we see that right away. We see this equation says v2 is 0. This third equation also says v2 is 0. Okay, so basically this third equation didn't matter at all. We already knew that v2 is 0. Okay, so we know for sure v2 equals 0. And if I plug that into our second equation here, that shows v1 plus v3 equals 0, or v1 equals negative v3. Okay, and here's where we have to make a choice, because we have only one equation left. We have 2 unknowns, v1 and v3, and that's okay. That's what we want. So in this case, generally what you can do is you just pick one of them to be 1. I'll say I pick v3 equals 1. That means v1 equals negative 1. All right, so we know v1, v2, and v3, so we can write down our eigenvector as negative 1, 0, 1 is our eigenvector. Okay. So that's how we solve it, and that also gives us one of the solutions is this vector, negative 1, 0, 1, e the negative 1 times t. Okay, that's a solution, the differential equation. All right, if we had made a different choice, you would get a different eigenvector, but it would still look like this. It would look like a multiple of this. Say I had picked 2 for v3, then I would have had negative 2. Okay, as long as I don't pick 0 and get all zeros, this is a valid eigenvector. Okay. Okay, so we just want to avoid having all zeros. Okay, so that shows us an eigenvector and it gives us our solution. And it's okay that this could be lots of different values. Okay, in solving an initial value problem, that's just the way we change this eigenvector is gonna change what our constant ends up being in an initial value problem. Okay, for a general solution, it doesn't matter because we're gonna throw a constant in front of here anyways. Okay, so the choice you make just changes the value of the constant for initial value problems. Okay. All right. So let's try a second one again. So now let's do 3. Lambda equals 3. Okay. So again, we have to solve that system of equations. Negative 1 minus 3, so we get negative 4. 1, 0, 1. Negative 1, 1. 0, 3, negative 4 times v1, v2, v3 equals zeros. All right. So again, I like to write these out as equations. We have negative 4 v1 plus 1 v2 plus 0 v3 equals 0. And we have 1 v1 minus v2 plus v3 equals 0. We have 3 v2 minus 4 v3 equals 0. Okay, so that's the 3 rows, just those 3 equations. You can try and just solve them, v1, v2, v3. So like I said before, one of these should be redundant, but it's not immediately clear which one of those that is. So just go ahead and just start solving them. So for example, this first one here, I can rewrite as v2 equals negative 4 v1, and I'll plug that into the other equations. So if I plug that into the second one, I get v1 minus v2, that would be minus 4, so that'd be plus 4 v1 plus v3 equals 0, which is the same as saying 5v1 equals negative v3. Okay, and then if you plug in this also to the third equation, so you do plug that in. So you have 3 times v2 is negative 4 v1 minus 4 v3 okay, is equal to 0. So we have negative 12 v1 equals negative 4 v3. Okay, so you move that across, you get 4 v3 on here. And divide that across. We get v3 equals negative 3 v1. Okay, I think I made this small. So these two equations, one of them should be redundant, like I said before. So looking at these two, they're not quite the same. I have a 5 and a 3, so I think I made a small arithmetic error somewhere. So let's quickly kind of look here. Make sure I wrote it all down right. Negative 1 minus 3 is negative 4. 2 minus 3 is negative 1. Here it is. So this is actually, when I move that 4 across, that should have been a positive 4. Okay, so this should actually be v1 minus 4 v1. And so we have a negative 3. And we move that across negative, so this becomes, both those become positive. So this is 3v1 equals v3. And if I plug that in here, this is positive now, positive, positive. I get 3v1 equals v3. Okay, so those equations match, those are redundant, so really only one of them matters. And so again, here's where we can make a choice. We have basically just these two equations. We have v2 equals 4v1 and v3 equals 3v1. Okay, so if we choose, for example, say v1 is 1, then v2 has to be 4 and v3 should be 3. So our eigenvector is 1, 4, 3. Okay, that's how we solve that for that eigenvector, and then that makes our solution x2 the form v2 e to the 3t. Right? That's our second solution. So again, you do the same thing basically now for lambda equals -2. You find your third eigenvector, and then the general solution is just constants, C1 times X1, C2 times X2 plus C3 times X3. So I'll leave that last one. You guys can try that on your own. But that's kind of conveys the main idea of that type of problem. All right. Here's another one. Okay. So in this case, again, the first step is always eigenvalues, eigenvectors. So we're trying to find the determinant, 12 minus lambda, -9, 4 minus lambda should be equal to 0. Okay, this is the same as saying determinant a minus lambda I used to be 0. All right. So again, a 2 by 2 is just the main diagonal minus the reverse diagonal. So it's 12 minus lambda times minus lambda minus -36, so plus 36, 0. All right, so let's distribute this out. We have lambda squared minus 12 lambda plus 36 equals 0. So how do we factor that? We want something to multiply to 36 and add to -12. That's going to be lambda minus 6 twice. Okay, so if you square this, you get -6 plus -6 is -12, and then -6 times -6 is plus 36. So that shows us that our eigenvalues is 6, but it's repeated as multiplicity 2. It's twice, right? Okay, so in this case, again, we still need to find the eigenvectors with that. So we need to solve 12 minus 6 is 6, -9, 4, -6 times v1, v2 equals zeros. Okay, so writing this as equations, we have 6v1 minus 9v2 equals 0, and 4v1 minus 6v2 equals 0. So if you say solve for v1, so we have 6v1 equals 9v2 divided by the 6. 9 and 6 is the same as 3 halves, 2. We plug that in, we get 4 times 3 halves v2 minus 6 v2. 4 divided by 2 is 2. This becomes 2 times 3, which is 6v2 minus 6v2 is 0 equals 0. Okay, that's good. That means that these two equations are equivalent to each other. Okay, and you can kind of see if you just multiply the second equation by 3 over 2, we get the first equation. So these are a redundant equation. That's what it's supposed to happen, right? So we still have to make a choice, which is good. That's what we want. So in this case, for example, if we say v2 equals 1, then v1 is going to be 3 halves. Okay. So sometimes what might happen in this repeated eigenvalue case is you might end up with even more choices. So you might have ended up in some case where these equations basically just turn into 0, 0. 0 equals 0 and 0 equals 0. And in that case, basically we have 2 equations, or we have no equations and 2 unknowns, which means we get to make 2 choices. Okay, and in that case, we would end up with 2 different eigenvectors. So if in this 2 by 2 case, you can make 2 different choices, you just pick 1, 0, and 0, 1. Those are your 2 eigenvectors. And because you can choose whatever you want for v1, v2, you just don't pick them so that pick them linearly independent and pick them so they're not zeros. Okay, and that's you can make lots of different choices, but this is kind of the standard. In that case, you end up with your solution, your general solution, just looking like this times e to the 6t times this times e to the 6t. Okay, however, in this case, we only had one choice to make. We ended up with one equation, 2 unknowns. So we only had one choice to make, which means we only get one eigenvector out of it. We only get the eigenvector 3/2, 1. Okay, that's our eigenvector, v1. Okay, so this means, as I said before, that we need to somehow find another solution that's linearly independent. And how do we do that? So this tells us part of the solution. The other part of the solution is now we need to solve a minus 6 times I times b2 equals v1. So we take our eigenvector we had before, we move it to the right-hand side, we resolve the equation. And that's going to give us v2. Okay. So let's do that and see how that happens. So we have the same matrix, 6 minus 9, 4 minus 6, times components equals, now our 3/2 are 1. All right, so this says 6v1 minus 9v2 equals 3/2, and 4v1 minus 6v2 equals 1. Okay, so again, these equations are redundant as well. So if you multiply the second one by 3/2, you would get the first equation. So we make a choice again. So for example, we can choose, say, v1 to be 1. In that case, we get 6 minus 9v2 equals 3/2. Let's subtract the 6 across. We get minus 9v2. 3/2 minus 6 is 4.5. So that would be, let's just say 3/2 minus 6. 6 is really 12/2. So you get minus 9/2. Okay, and then you divide the 9 across. That means v2, negative 9, cancels out the negative 9, we get 1/2. So our second eigenvector, or second vector, not an eigenvector, is v1 is 1, v2 is 1/2. All right, so we found those two vectors. Now we use our formula that we can look up to say that the solution is c1 times our original eigenvector, so 3/2 1 t e to the 6t, plus c2, our second vector, 1 1/2 e to the 6t. Okay, so again, what we're doing is we're multiplying by t, but that also modifies what these vectors are. So the original eigenvector goes with the highest power of t, and then each time we repeat, we have to find a new vector here that goes down. Okay, so this is v2 here. If you had to repeat it 3 times, you would move v2 onto the right-hand side, and you would have a plus. You'd have a plus v3 e to the 6t, and you'd multiply t, and you'd multiply by t over 2. So you'd have like each time the power goes up, and you kind of slide it over and add it on a new term. Okay, so you can look that up in the book as well for additional examples. But that's the idea. All right, now for our last example, it's going to be a complex case. So again, we need to find the eigenvalues. So that's solving this equation, 4 minus lambda, negative 5, 5, negative 4 minus lambda equals 0. So we get 4 minus lambda, negative 4 minus lambda, minus negative 25, so plus 25 equals 0. So distributing this out, we get lambda squared. We get a minus 4 lambda plus 4 lambda, those cancel. Minus 16 plus 25 equals 0. Or lambda squared plus 9 equals 0. Solving this, we subtract the 9 across, so lambda is plus or minus square root of negative 9 plus 3i. If we have a complex eigenvalues, and they came in a pair, right? So in this case, you can think about, in our original, we had alpha is the real part, which is 0 in this case. Beta is the complex part of the imaginary part, which is 3. Okay, so that means that we need to find the eigenvector that goes with lambda equals 3i. Okay, so that means solving this system here. It says 4 minus 3i minus 5i minus 4 minus 3i times v1, v2 equals 0. Okay, this is going to be complex numbers, and that's okay. So we have 4 minus 3i times v1 minus 5 v2 equals 0. 5v1 plus negative 4 minus 3i v2 equals 0. So as before, I said when you have two equations, they should be redundant. Okay? We should have at least one equation go away, and have to make a choice. It's not immediately clear that this is redundant, that these are the same equation, but you can actually show that by multiplying by a conjugate. So in this case, if we multiply by the complex conjugate, so 4 plus 3i to the first equation, minus 5 times 4 plus 3i. Okay, and simplify. So we have 4 times 4 is 16. 4 times minus 3i is negative 12i, but then we have a plus 3i times 4 is plus 12i, those cancel. Then we have 3i times negative 3i. So it's going to be minus 9. I times I squared is negative 1. Okay, so it's going to end up being plus 9 v1. And then we just distribute that. We have plus negative 20 minus 15i v2 0. And this is 25. Okay, if we compare this to the second equation, we see that if we multiply this equation by 5, you'd end up with this equation. So these equations really mean the same thing. Okay, so in practice, you can just kind of ignore one of these. Just assume if you did it right so far, these two equations here are telling you the same amount of information. So you just pick one and try and solve that. So if I pick the first one, I have 4 minus 3i v1 equals 5v2. Okay, and then you can pick a number, say, if you pick v1 to be 1, then you can solve for v2. One thing that kind of works out nice is if, say, we pick v1 to be 5, then we can divide the 5s across, and v2 then should be 4 minus 3i. Okay. Kind of v2 becomes this term, and v1 becomes this term here. Okay. And then they become equal products on both sides. So that means our vector is 5 over 4 minus 3i. Okay. And again, lots of different multiples of this are also eigenvectors. And in fact, since it's complex, you can have like complex multiples of it as well would be eigenvectors. So if you have you might end up with a complex number in the first term versus the second term, and that's okay, as long as they're multiples of each other. It's just a lot less clear in this complex case. So basically, we've done all the hard part now. We found the eigenvector, we know the eigenvalue, and we can write down two different equations, basically just using our formula from before. So x1 becomes, first of all, let's find the real and imaginary parts of that vector. So the real part of this vector, 5, 4 minus 3i, is the vector 5, 4. And the imaginary part of that is, there's no imaginary part in the first term, so it's 0. And then we have minus 3 in the second term. Okay, so the first solution again, like I have to look this up every time, and that's okay, is the real part of the vector. So it's going to be 5, 4 times cosine of beta, which is 3t, minus the imaginary part, minus 0 minus 3 sine of 3t, all times the exponential e to the alpha t. Well, alpha is 0 in this case, so that would just be e to the 0t, which is just goes away as just 1. Okay, so it's just the sines and cosines. And the second term is the imaginary part, so 0 minus 3 cosine 3t plus the real part, 5, 4 sine 3t. Okay. Those are the two solutions. And our general solution, is C1, X1, C2, X2. Okay. So that's how you would solve a complex eigenvalue case. So in general, if you had like a really big system, say it was like a 5x5 or a 6x6, you could have lots of different, so you could have a few distinct, you could have one repeated, you could have some complex all together. Whenever you have that eigenvalue, that case, you just find the eigenvector, you find the solutions that go with that eigenvalue, and then in the end, the general solution is just adding all those together times by constants. Okay, so however many eigenvalues you have, that's how many different solutions you should get, and at the end you just multiply them by constants and add them together to get the general solution. Okay, that's kind of the nice part about the system. That's why linear makes it nice. If this a was non-constant or if this was nonlinear, everything just goes out the window and we can't do any of this anymore. But in this case, it's nice things happen, and you should all kind of be familiar with how to do these eigenvalue eigenvector problems, what that tells you about the system here. Okay, so I mean this really shows you, I guess, last kind of thing I want to say is that the eigenvalues and eigenvectors of a matrix are really important properties of that matrix. They show you something about the behavior of this system. So if you have like a matrix with all negative eigenvectors or eigenvalues, you would kind of see that we have this, the solutions are all e to the negative t, and they're all like kind of these decaying functions. And that tells you something interesting about the matrix, about the system here. And it's not exactly obvious, that you might end up with negative eigenvalues. Even if a lot of the terms in A are positive, what really matters is not the values of A, but the eigenvalues and eigenvectors. Okay, that's what tells you about the behavior of the system. All right, so on that note, I'll end there. Feel free to email me if you have any questions, and hope you have a good end of the class.